Welcome to Study Loop.
Once again, welcome to a new problem. This time we're given, it's almost like chemistry where we have a neutron that breaks up into a proton and an electron. And it just so happens that the mass of the proton is equivalent to 1,836 times the mass of the electron. So this is the mass of the electron. And so there's energy released in the process. Okay, so there's energy released. So we want to know, um, what fraction, what fraction, uh, fraction of the total kinetic energy is the kinetic energy of the proton. So in relative terms, obviously you're seeing that, the mass of the proton is 1,836 times the mass of the neutron, and that affects the kinetic energy. So, the first thing we're going to do is to use the law of conservation of momentum. We'll use the law of conservation of momentum that says the initial momentum of the system equals to the final momentum of the system. Initially, you only have the neutron like that, and then this is like before, and then after you have the proton and the electron. This is what happens after. So after there is motion, before there is no motion, and so the initial momentum is zero. The initial momentum is zero. And the final momentum is going to be the velocity. As they're moving, you could see that the proton is going to have its own velocity, and then the electron will also have its own velocity. The proton has the proton will have its velocity, the electron will have its velocity. Remember, the electron is negative, so we'll have zero equals to the mass of the electron. The momentum of the electron is negative, but the momentum of the proton is positive. Remember, the electron has negative charge and the proton has positive charge, and so this will help us solve for the velocity of the electron. So mp mv, this is pure algebra. We divide both sides by the mass of the electron. So we see that the velocity of the electron is the ratio of their masses. That's why this number is very helpful. The ratio of their masses times the velocity of the proton. It kind of like makes sense. If one is huge, then it's probably going to move slower. And then if one is small, it's going to move faster, relative velocities. In the next page, remember our target is to get what fraction of the total energy, total kinetic energy of the proton what fraction of the kinetic energy of the proton is it what fraction of the total energy, it goes to the kinetic energy of the proton. So on this side, we kind of have the total energy. And then on this side, we have the total kinetic energy. We have the kinetic energy of the proton plus the kinetic energy of the electron. So that's what's going to happen. In the next page, we have the total kinetic energy of the system is split. This is kind of like what's in the neutron, and it's split into the kinetic energy of the proton. This is the proton, plus the kinetic energy of the electron. This is the electron. And so the total kinetic energy becomes the same as 1/2 mass of proton times velocity of proton squared plus 1/2 mass of electron times velocity of electron squared. That's what we have. Remember, previously we were able to get the velocity of the electron, and we can do the replacement and say this is equal to 1/2 mass of proton, velocity of proton squared, plus 1/2. The mass of the electron is the ratios of the mass of the proton and the electron times the velocity of the proton. And this helps because now everything is in terms of pretty much in terms of protons, with the exception of the mass of the electron. But that's good because on a relative terms, we know what the mass of the proton is relative to the electron. Okay, so it means that we could still solve our problem. So going back, we simplify this and say 1/2 mass of proton. Remember this one, this velocity, this velocity of the electron. So let's go back. Velocity of the electron is this one. So we have to square that. And then we have the mass of the electron there. So we have 1 mass velocity of proton squared plus 1/2 mass of electron times mass of the proton squared, like that, over the mass of the electron squared, and then velocity of proton squared, like that. This one also is squared. So this will cancel one of these, and we're left with 1/2 mass of proton, velocity of proton squared, and then 1 plus mass of proton over mass of electron. So this is just pure algebra. And so in the next page, we notice something special. When you see this one is the kinetic energy of the proton. So we're going to use that in the next page. And so the total kinetic energy of the system equals to the kinetic energy of the proton, which is this part, and then times 1 plus mass of proton over mass of electron. And then we can divide both sides by the kinetic energy of the proton. Okay, kinetic energy of the proton. And we wanted to find out in relative terms. We wanted to find out in relative terms what's the kinetic energy of the proton relative to the total. So we have total over kinetic energy of the proton, like that, equals to, these two cancel out. We can put a common denominator there, mass of electron. So we're multiplying both sides by me over me. So this is mass of electron plus mass of the proton. And then we're going to flip it because we want the fraction. So kinetic energy of the proton over the total kinetic energy becomes the mass of the electron over the mass of the electron plus the mass of the proton, which is the same as, if you go back here, we're interested in the totals. So the mass of the proton is 1836, the mass of the electron. So we'll have mass of the electron over mass of the electron plus 1836 mass of the electron. We simplify that, we get mass of the electron over, this is like having a 1 there, so 1837 mass of the electron. These two cancel out. And then it means that finally we can say that the kinetic energy of the proton relative to the total kinetic energy of the system is 1 out of 1,837. If you multiply that by 100%, we see that the fraction is 0.054%. Hope you enjoyed the problem. If you have any questions, send them my way. The deal here is to remember the fractional relationship of the masses and then to use the law of conservation of momentum. Before, nothing happened. Afterwards, there was motion that helped us to solve for the final velocity of the electron. And then we plugged in those values to look at the fractional relationship. So we used the kinetic energy. The total kinetic energy is the kinetic energy of the proton and the electron. So using that in algebra, we're able to get the fractional relationships. Okay, so if you have any questions, send them my way, and have a wonderful day.